joining us for the first time. Saksham, this is Daniel. Hello. Today's lesson will be an interesting one. We will be learning linear algebra, so some matrices, vectors, and then Daniel will give you an overview of data visualization with the Titanic dataset. Yeah. So how many of you have studied linear algebra before? Since it's a small class, maybe everyone. Okay, so that is like everyone. Should we go?
Who hasn't? Right, so everyone. Okay, do the hard things. Do the. So let me just. Okay, so everyone has done linear algebra, yeah?
Linear algebra is almost.
Okay, we'll become more.
First year maths, yeah. Everything?
Like
No, sure?
vector addition, multiplication.
Yeah, just
dot products.
A quick
cross
refresh
products.
would be helpful for me at least.
Oh yeah.
Oh, okay.
But we want But
Yeah.
we only need to go to like the super easy. Are you like 100% sure no one needs like a super easy introduction? No.
Because we'll need it later in machine learning. So.
To what? Oh wait.
Oh, just start from super easy. Yeah.
Okay.
Quick overview of the easy.
Guys, if we could just use the right-hand board. Yeah.
Okay, we'll start there. Okay, so we'll start with do you want to go through addition and subtraction, or is that like self-explanatory?
Should be obvious.
Just start from the beginning.
Okay, because when we did the survey, like
People are online, George. People are online.
Yeah, start from the beginning because people are watching online.
oh yeah, true. Okay,
Yeah. Maybe
so
it's
we'll
good.
start with addition and subtraction of matrices. Before we do that, we'll just revise the definition of a matrix. So a matrix is just an array of numbers. It's useful in machine learning because that's how we represent our data, but it's especially used in physics and other areas of math. So basically, if we have a matrix A, 2, 1, 3, 4, 6, 8. So an m by n matrix is a matrix with m rows and n columns. So in this case, this is a 2 by 3 matrix because it's got 2 rows and 3 columns. And when we refer to specific elements in the matrix, it's denoted by aij. This is the ith row and the jth column of the matrix of A. So for example, A 2, 3 is the second column and the third, so it's A. And similarly for all other elements. So now we'll go on to addition of matrices. So you have two matrices A and B. Addition is only defined when their dimensions are the same. So if A is a 2 by 3 matrix, then in order to add and subtract with another matrix B, the dimensions of B must also be 2 by 3. We'll find out why for obvious reasons. So 2, 8, 9, 8, 7, 6. So then A plus B is defined as, you basically add the corresponding entries. So 2 plus 2, we have 4 here. And likewise 9, 12, 12, 13 and 14. So this is A plus B. We simply add the two matrices, their corresponding elements, and you can see why addition with different dimensions doesn't work. So 2, 3, 4, 5 plus 1, 2, 3. This isn't defined because they have different dimensions. This is a 2 by 2 matrix. This is a 3 by 1 matrix. And there's no corresponding elements for this row and this column. So, and subtraction works on the same principle. You add these to get these corresponding results and subtract when you're doing matrix subtraction. So that should cover all of that. Now we'll go on to, that's fine, right? Everyone knows that. Yeah. So now we'll go on to multiplication of matrices, which is defined a bit more uniquely. So if we have two matrices 2, 3, 4, 5 times 1, 2, 3, 4. It's not simply the, as with addition and subtraction, it's not simply the multiplication. We don't simply multiply the respective elements and end up with a result. So this is not 2, 6, 12, and 20. So instead we have to, it's defined differently, and we'll look more into that. So basically, if you have an m by n matrix, in order for multiplication to exist, we need to multiply it with a matrix which is n times something, r, which basically means the number of columns in the first matrix has to be equal to the number of rows in the second matrix, or in other words, these two must be equal. And the resulting matrix will be an m by r matrix. M by r. So to sum up multiplication, not to sum up, just for the rules. In order for multiplication to exist, for an m by n matrix and an n by r matrix, we require the number of columns to equal to the number of rows in the second matrix, and the resulting will be m by r matrix. Or if you want to call that s, some arbitrary number s, then if n equals s, then multiplication is defined. So how do we actually multiply matrices? Well, we look at the row vector of the first matrix and the column vector of the second matrix firstly. So here we see 2 and 3 and 1 and 3. And then, so this entry here will be 2 times 1 plus 3 times 3. That will be the first entry. Just write it here. So here we have 2 times 1 and 3 times 3. We're basically taking the dot product. And the element here, so what we do now, we take the second row, the second column, and repeat the same procedure with this row. So we do 2 times 2 plus 6 plus 3 times 4. Okay, so now we have the first row done. Now we look at the second row. So we take 4 and 5 and 1 and 3, the second column, the second row space, and the first column space of the second matrix. And this element here will be 4 times 1 plus 5 times 3. And finally, the last element, we look at the second row, second column of the second matrix. So that will be 4 times 2 plus 5 times 4, which is 9 plus 2, 11, 19, 16, 28. And that is the result. And as you can see, it is an m by r matrix. So here we have a 2 by 2 matrix and a 2 by 2 matrix. So we check the inner two terms. They are equal, which means multiplication is defined. And the outer two terms, it's an m by r matrix, 2 by 2. And as you can see, this is a 2 by 2 matrix. That is matrix multiplication. We'll do another example with different dimensions. Okay, so an m by n matrix times an n by r matrix. So we'll say 3 by 2. And now the second matrix, n must equal 2 to satisfy the multiplication condition. and we'll say 2 by 1. R can be anything. So first we check if it's defined, and yes it is, because 2 equals 2. And the resulting matrix will have dimensions 3 by 1. So let's just choose an example. So we have a 3 by 2 matrix, 1, 2, 3, 2, 1, 3, times a 2 by 1 matrix. So 2, 4, yeah. So 3 by 2, 2 by 1. Once again, it is defined because the number of rows here is equal to the number of, the number of columns here is equal to the number of rows here. We have 2 columns, 1, 2, and 2 rows here. So it is defined. And the resulting matrix will be, as we said earlier, an M by R matrix. So a 3 by 1 matrix. This will be a 3 by 1 matrix. And we apply the same procedure as we did before. We take the row space here and the column space here, column vector. And so we have 1 times 2, 2 plus 2 times 4, 2 times 4. And we take the second row vector, do the same thing, 2 times 2, 4, plus 1 times 4, 4. And finally with the final column vector, row vector, 3 times 2 plus 3 times 4. So the result is 10, 8, 18, which is, as we said earlier, a 3 by 1 matrix. And that sums up matrix multiplication. So the key thing to remember is if you're multiplying an n by n matrix with another matrix, the dimensions must be n by some arbitrary number r. As long as the inner two are equal, matrix multiplication is defined, and the resulting the resulting matrix will be an m by r matrix. That's multiplication. That's vector multiplication. There's also scalar multiplication, which is simply where you multiply a matrix by some quantity, so 2, 3, 4, 5, times some scalar, we'll call it lambda. That is simply 2 lambda, 3 lambda, 4 lambda, 5 lambda. So when you're multiplying by a scalar, it's just normal multiplication. So that sums up addition, subtraction, multiplication. Now we will go into the determinant. Do you want to do it? Okay, so do you want to go into...
No. Wait, okay. I'll let you do it, please. Give me a second.
Okay.
Okay, so as you know, Saksham was explaining matrix multiplication. He showed you how, okay, so let's start. I think he forgot to mention, so since most of you know what a matrix is and stuff, you probably don't, probably in maths, you just know them as numbers, right? They're just a random, a matrix is just 1, 2, 3, 4, right? You probably you got taught in maths that they're just numbers which represent a linear combination. So this is A is equal to bar, right? So in essence, in computer science, right, they don't treat a matrix like this. They treat it more like an array of just random numbers. So they treat it more like a table. So pretend I have a table which is fruits, right? And this is number of fruits, yeah? And then the first fruit is apple, and then orange. And then the number of apples in my fruit basket is 2 and 4, right? So in computer science, how do we translate this into a matrix? How do we change this into a matrix format, into maps, right? We obviously know that the 2 and 4 is fine. But what do we do with these? What do we do with this apple and orange? Do we just write apple and orange? That's not a matrix, right? These have to be numbers. What are we going to do? Does anyone have any suggestions?
Encode it.
Huh?
We encode it.
Yeah, encode. So what would you like to encode? So what does apple equal to?
0.
Okay, and orange?
1.
Correct. We encode it. And this is called conversion of categorical variables. So what happens if we have another one, apple? What's the next one? What's the next row? Yep, 0 and 1. Exactly. So this is a matrix in computer science. It's not the same. It's kind of similar to maths, but it's not exactly the same. And also Saksham said multiplying matrices. How do we multiply matrices? Like what is even multiplying matrices? Do we just multiply matrices for no reason? So Saksham was talking to you about how you multiply the column space and the row space. So if you visualize it, right, if I have another matrix, 2, 3, 4, 5, and I want to times it by, let's say, a vector. So a vector is just a one column matrix kind of, right? Let's say I want to times it by 1, 2, right? Is this allowed? Can we do this? But why is this allowed? So what you do, what does matrix multiplication actually look like? What we do is we make this vector, right, and we transpose it and we put it on top. This is actually what it looks like, right? Does this fit? Does the matrix on top fit with the bottom matrix? If yes, then this is allowed. If it's no, it's not allowed. I'll give you an example. So if we want to just times it by 1, right, just the number 1, if you use matrix multiplication, if it's just a matrix, it's not a scalar, so a scalar is just a number. But if this is a matrix, let's do the same thing. We get this, we put it on top. Does it fit? No, which means it's not allowed. So the matrix must fit. Right? So pretend I want to times it by 0, 0, 0, 0. Yeah? So do the same thing, we put it on top, and it exactly fits. It fits, so this is allowed. But how do we actually times it? So Saksham was saying how you do you have to match the elements. So how do we actually match the elements in a more intuitive sense? So once you know it fits, we shift it over. Right? We shift it over. And what you do is you just do this. Right? The top row must go with the first column, and the last. So like this, right? If you have another row, you just keep going like this, right? And how do we do it? We just get the first element and times it, right? What's 1 times 0 is 0, right? And you just add it, right? And then, wait, don't do it, right? Yeah. So you add these things, right? So 0 times 1 is 0, 0 times 2 is 0, so you just add it, 0. Right, and so on. 0 times 1 is 0, 0 times 2 is 0, add it, 0. And so 0, 0, 0, 0. Right, so this is what you do. Yeah.
Yeah, so basically, did you explain the transpose?
Oh yeah, in the usually it was transpose.
Okay, so Daniel just taught you the transpose basically. He showed you a process called transposition. We were meant to teach that next week, so. Anyways, we'll move on to the determinant and to the deriving now.
So do you guys understand matrix multiplication and how it works? And yeah, okay.
Yeah, so what he basically showed you was the conversion of categorical variables. When we're dealing with matrices in data science or in computing in general, we have to basically quantify our variables. For example, a computer can't do operations on the variable apple because it doesn't recognize it. So by converting it numerically, we can do those operations. So now we've done addition, subtraction, multiplication. Division isn't defined for matrices. So now we will move on to the determinant.
Oh, so wait. So when Saksham said division is not defined, he means that if you divide a matrix by another matrix, right, it doesn't really make sense, right? How do we divide matrices? But in computer science it's allowed. And why is it allowed? Well, it's called dot division, right? You divide by each element. So element-wise division, in some, if you see like some, I think math notation just looks like this. I think it's a circle with a thing or a divide sign inside. So you do element-wise division. So in fact, you can do this. Obviously, this is not allowed, right? 1 divided by 0 is not allowed. But yeah, you can do that.
It has to be non-zero, yeah.
Yeah. But technically you can. It's called the inverse. But we will describe, determinant. Yeah, that's all, yeah.
So, I don't know if this is defined in maths.
It is. Those things are.
Oh yeah,
But You won't see it in maths because they don't like it.
So now we'll move on to the determinant. We'll start with a 2 by 2 matrix of a 2 by 2 matrix. So if you have a matrix, let's call that A, B, C, D, the determinant is defined as, well, firstly the notation is determinant of A, or more commonly mod A, like absolute value symbol, is defined as AD minus BC, simply. So the determinant of 1, 2, 4, 8 is 8 times 1 minus 4 times 2, which in this case is 0. And that's simply the determinant of a 2 by 2 matrix. Now when we do a 3 by 3 matrix determinant, it's a bit more complicated, but same procedure. So if we have a 3 by 3 matrix, let's say,
You want to explain what is the determinant?
we'll come back to that.
So
We'll explain its meaning in inverse when we're doing inverse.
Yeah, but you still. So do you guys know actually what is a determinant? Like you get it, like you know the A, B minus D, C, but what actually is a determinant? Do you know? So
It's actually to do with, so say if you have a matrix defined in 3-dimensional space, it basically, there's a visual representation, I obviously can't draw that here. It basically shifts everything by a factor of the determinant visually. But that's more into physics and we probably don't want to go there. But if there's...
in essence, it's the area, right? So if you find the determinant, like you know when the determinant is equal to 0, we can't find the inverse. Why? Because the area is 0. How can you find the inverse of a matrix if the area is 0? What's the inverse of a 0 area? I don't know, right? So, no, that's not 0. Because the inverse, right? What's 0 divided by, it's the division, right? It will have to be 0 divided by 0.
You can't take the inverse of a matrix with determinant 0.
Yeah. Well, actually you can. But anyways, keep going.
Can you?
Yeah, you can. It's called pseudo-inverse.
Okay.
Yeah, I don't think so you did. That's way too. I don't think so we need to do the determinant of 3 by 3.
Do it anyway.
That's way.
Okay, so it's just do it. So it's simply, you can memorize it, or there's a very simple way of deriving it. So we take the first element A, and then the determinant of the submatrix, like if you think about covering this whole row and column, E, F, H, I, minus B times the determinant of D, F, G, I, plus C times the determinant of D, E, G, H. And we established how to do these 2 by 2 determinants earlier. And for higher dimensions, like 4 by 4, there's computer software to do that. I wouldn't waste time doing it by hand.
Or you can row reduce and just times all the...
Yeah, if you know row
elements.
reduction, you can do that. But like, it's not worth
Yeah,
doing
yeah,
by
yeah.
hand.
If you know, yeah.
Because there's a lot of open source software which does that for you.
Just go to inverse.
Inverse?
Yeah.
Okay. So when we talk about the inverse of normal numbers, so basically when we're dealing with scalars, we have 5 times inverse of 5 is 1, essentially. In terms of matrix multiplication, so normal multiplication, we have a number A times 1 on A. It's always 1. So with matrices, we want to, I'll introduce the identity matrix first. So the identity matrix is a matrix with all diagonals 1 and 0 everywhere else. So if we have a 3 by 3, it's 1, 0, 0, 0, 1, 0, 0, 0, 1. And that is the identity matrix. So basically we want to see if we have some value B such that A times B is the identity matrix. Oh, and one more thing about multiplication of matrices, it's generally not commutative. So if you have A times B, in general, it's not equal to B times A. for obvious reasons, which we established earlier. An m by n matrix can only be multiplied by an n by r matrix. If you reverse that, it's not true, necessarily. So we want to find some value b, some matrix b, such that So we want to find some matrix B such that when you multiply it with matrix A, you get the identity matrix. So for 2 by 2 matrices, we have a very easy formula to remember. So if you have A, B, C, D as A, we want to find A inverse. It's simply 1 on the determinant of A times. So what we do, we switch these two and we change the sign of these two elements, C and B, so minus C and minus B, and that is the inverse of A. So we can find out here that if the determinant of the matrix is 0, clearly it's not defined. The inverse is not defined, unless Daniel wants to explain.
Yeah, I'll let, yeah,
Okay.
I'll tell you later.
Do you want to do it now?
No, not now, no.
Okay, so basically, this is the inverse of a 2 by 2 matrix. It's got a formula, but if you have higher dimensions, you can just use row reduction and figure that out from there. If you know row reduction, we're not going to cover it here because we have software to do that, so it's not necessary. So we'll run through an example. This is also there. So for example, if we have A equals 2, 1, 3, 4. So we want to find some matrix A inverse such that A times A inverse will result in the identity matrix. So how do we do that? Well, we find A inverse to be 1 on the determinant of A, which is 8 minus 3, which is 5, times, as we said there, switch these two, so 4 and 2, and reverse the sign of the 3 and 1. So minus 3, minus 1. So that will give us the matrix 4/5, minus 1/5, minus 3/5, and 2/5. So that's our A inverse, and you can check by matrix multiplication. If you multiply A and A inverse, you will get the identity matrix, which will be a 2 by 2 matrix. So, do you want to do the multiplication? No? Okay, so,
Just say it.
yeah. As we did with matrix, with the multiplication earlier, if you times this by this, you will get 1, 0, 0, 1. You can try that. We're not going to do that here, but it will work. So A times A inverse will give you the identity matrix, which will be 2 by 2. And so that covers determinants and inverses. So we'll move on to cross and dot products. Unless you want to explain.
Okay, so Saksham was explaining to the inverse. So I think probably people will think like, okay, you get it in maths, you want to solve equations by using the inverse and stuff. So why is it actually like, do we actually need to use it in real life? Like, what's the whole point of inverse, right? Who cares about a stupid inverse? A times A inverse equals I, right? So what's the whole point? So you know in maths, like if you just do normal numbers, right? So 3, right? What's 3 times 1/3? Yeah, that should be easy, right? 1, right? 1. That's easy, right? So what's A times 1 over A if A is a matrix? Is it not defined? Just think about what this one divide means.
It's the one thing, the one identity matrix thing.
Yeah, it will be identity technically. We want it to equal to this, right? We want it to equal to this. Or we want it to equal to 1, kind of, right? So we want maps to extend to matrices. And in fact, we can't, this doesn't make sense, remember? Like, remember I told you the dot division? If it looks like this, then we're technically doing dot divide. We're dividing every single element by the matrix A, which is not allowed, right? So we change the notation and it has to look like this. We do this. We kind of cheat, okay? And this is what it actually means. It's the same thing as this, technically, but not really. We can't write this, okay? That's not allowed in maths. They'll hate you if you write that. You have to write this, right? So A times A inverse equals I. And similarly, 3 times 3 inverse, right, is also 1. It's the same thing. Just you have to use this notation. Okay, so remember we were talking about how if the determinant is equal to 0, right, the inverse does not exist, or does it? Right? So sometimes in math, sometimes in computer science and some other applications, what happens if the matrix actually is equal to 0? What are we going to do? We can't do anything, right? We just stop, oh, it's 0, we can't solve the equation, right? That's hopeless. So remember the apples and oranges thing? So like, just do this, right? What's the determinant?
0.
Right, it's 0. But we want to solve the equation, like remember we want to solve it, right? Pretend we want to solve it equals to 1, 1, right? What are we going to do? Do we just say, oh, you're not allowed to do it because the inverse doesn't exist? We can use, but remember it will be 0, 0, 0, 0 if you use row to reduction. It will be infinite, right, solutions, right? But do we just stop there? Is there actually really infinite solutions? No, right? There actually should be a very close solution. And we will probably do that later. But I think yeah, okay. We will have to do transpose. Yeah. Give me a second. So we're going to do this next week, but I think we should do it now because most of you know some maths. So if we have a matrix 1, 2, 3, 4, right? And I want to change the rows and columns, right? How do we do that? Like do you know what's the so the notation is transpose, which is a T, right? And this is equal to, so what you do is you look at the first row, and then you just make it a column. You look at the second row, you just make it a column. And this is the transpose, right? So why do we use transposes, right? There's another question. What's the whole point of transpose? So I get this, but why do we need to do it anyways? So, in fact, it is useful. Actually, it's one of the most useful things you'll ever learn in maths, which is the transpose. If you forget everything else in maths, just remember your transpose. Why? I'll show you. And then we have to, okay, so if you're, okay, yeah. Okay, so before I tell you that, we need to talk about the orthogonal trick. Has anyone heard of that? No? Orthogonal trick? Or maybe I just made it up. Okay.
That with regression.
Yeah, no, we still need
with
it.
regression.
Yeah, but no, we just need to tell them. Okay, so the orthogonal trick says that pretend you want to find the inverse of a matrix, right? But it's not squared. What do we do? Right, so it's 1, 2, 3, 4, 5, 6. How do we find the inverse? We can't. Because if you find the inverse of a non-square matrix, so it's like, it's not square, right? It's like a rectangle, like a vertical rectangle, right? We can't find the inverse. So how do we find the inverse then? Do we just stop? Right, like before, if it's 1, 2, 1, 2, and we just stop, we can't do anything. No, we don't stop. We extend the definition. So how do we do that? Right, this is A, right? How do we find the inverse of A? What we can do is we use a cheat method. We times the transpose by A. Right, this is called least squares, but anyways, I'll just call it the orthogonal trick because you made it into like a orthogonal matrix. Anyways, what does this do? So using, like if you just make a smaller one, just 1, 2, okay? That's A, right? So to times, remember, we put it like this, and you just go down. So 1 times 1 is 1. 2 times 1 is 2. 2, 4. Right? 1, 2, 2, 4. Now this is square. Now you can take the inverse of this. And why do we call it least squares? Why do we call this least squares? If you didn't realize, this is squared, right? 2 times 2 is 4. It's squared. So that's why and then all of these we times, and this is orthogonal. Wait, not orthogonal. Wait, did I say it right? I think that's orthogonal. Oh, who cares? Anyways, we can now take the inverse of this. Well, technically not this, because the determinant is still 0. But you know what I mean. Okay, if you do A transpose A T to A, you will get a new matrix, and then you can take the inverse. So, okay, one more thing. Yeah, I think we should do, we should start on, Yeah, and machine, yeah, I think we should start on regression. I think we should. Okay, anyways, but now you learn all of this, okay? So how are we going to apply it? So we're going to introduce you the first ever machine learning algorithm, okay? And it's called linear regression. Like you probably learned it in Math 2501 and Math 1241 or whatever, right? Or economics and stuff, right? So linear regression, what do we want to do?
Or YouTube.
Oh, what?
YouTube.
Oh, YouTube, yeah. Wait, is it all dying? Horrible. Okay, anyways, so what is linear regression? Okay, we are going to, I think in maths courses, you did some, but they don't actually tell you what's the whole point, okay? They'll just say, oh, you can do this, whatever, who cares? Okay, so pretend I want to predict house prices, yeah? And I have, okay, this is house prices is here. And this is the land size, okay? I want to predict, using land size, I want to know what's the house price. Okay, so it kind of looks like this. As the land increases, let's just say the house prices increase, okay? So what least squares, what linear regression tries to do, as the name suggests, we want to fit a straight line, okay? So that's easy, we can just draw it, yeah? Super easy. So then we can predict what's next. Obviously this is incorrect. What happens if the land size is negative? Does it even make sense? No. But anyways, that's what linear regression does. But the question is, how do I find the line? Right, if you remember your high school maths, you can get the equation of the line using y equals mx plus b, right? But this is only for 2 points. What happens if there's 10 billion points? What are we going to do? So, we use all the things we learned today to make something. Right? So my question is, let's draw, okay, so instead of the house prices, let's just do apples. Okay, so how about,
Use this one.
is that, okay, apples, wait. No, wait. Oh, okay, apples. No, this is kind of horrible as well.
Try one of these.
Oh, the, what? No, wait, what? Just use this. Oh no, this is okay. Okay, apples. I have apples, right, and I have 1, 2, and 0, okay? 1, 2, and 0 apples. And I also have oranges, okay? And I also eat 1, 2, and 0. So this is how many I eat, and my happiness level. Right? So let's say that if I eat 1 apple and 1 orange, I'm not happy at all, okay? If I eat 2 apples and 2 oranges, I'm, I don't know, 10 happy. And if I eat 0, I'm 3 happy. Okay, this kind of doesn't make sense, but who cares? Okay, let's just say this. Okay, let's say that I want to find a line which fits this, right, the predictors to the y values, right? So in statistics, if you did some statistics, this would just be called y, right? This is your target variable, and your input variables are just called x. Okay, anyways. Right, so I want to find something which lets me go or maps from x to y. I want something which gets these input variables and I find some y. But how am I going to do it? So using the things we learned today, in linear regression, what we want to do is we want to assign a kind of constant to apples. So we want something like this. We want something, right? Is it like anything else or they're all dead? Okay, I have to. Okay, fine, anything. Okay, so so what we want to do is I want something, right, times apples, plus something times oranges is equal to happiness. I want to find these somethings, right, and how do I do it? Well, because we learn matrices, we can extend it, right? I want 1 times apples, 1 times A, so A will be the apple constant, plus 1 times orange, right? And this has to equal to 0, and so on. Right, this is what I need to solve. I need to solve these equations, right? And how do I do this? Well, we learned in matrix multiplication that in fact, you can make this system into a matrix. And how do we do that? Well, we just get we just get the 1, 2, 0, 1, 2, 0 in a matrix, 1, 2, 0, 1, 2, 0, right? And what do we times it by? What do we times to get 0, 10, 3? We times it by, so if you use the same method, we times it by A and O. Right? See look, 1 times, so A plus, so 1A plus 1O, 2A plus 2O, and so on, right? And this, in fact, is 0, 10, 3. And this is what we need to solve. We need to solve this equation. We need to solve 1, 2, 0, 1, 2, 0 times AO is equal to 0, 10, 3. We need to solve this equation, right? We need to find A and O. And what do we do? Right? So, we use our concepts of least squares and stuff to solve the equation. I'm going to make these 1, 2, 0, 1, 2, 0 equal to A, okay? So A...
Wait, do you want to show them least squares first, like graphically?
Oh, it's okay. It should be fine. Yeah, I'll show them, yeah. Okay. So A is equal to 1, 2, 0, 1, 2, 0. Oh, this... I need to get more pens. Okay? And... Oh, sorry, not A. Sorry, I'm going to call it X, because I'm going to copy the statistics one, right? So X is equal to 1, 2, 0, 1, 2, 0. And the parameters, so the A0, we're going to call parameters. And in machine learning everywhere, the parameters are going to be denoted as theta. Okay? Okay? Theta is the parameters. Oh, okay, thank God. Okay, this is good. Okay, theta is going to be your parameters, A0, okay? And your target variable y is 0, 10, 3. And we want to solve x times theta is equal to y. We want to find the parameters theta. And how are we going to do that? Remember, step 1, this is not square. How do we change it to square? What are we going to do? Yes, transpose. We times it by the transpose. Right? Cheat method. But because we did this on one side, we have to do it on the other side. Right? And now we can take the inverse, right? We can change this to I, the identity matrix. We can take the inverse, right?
And also, when you... one thing important to remember, when you multiply, it has to be in the correct position.
Oh yes, correct.
Because it's
Not
not
commutative.
commutative.
So whenever you do stuff on the left side, you have to put it on the left side. If you do it on the right side, you have to do it on the right side. Too bad, you just have to do that. Doesn't work. So, okay, because we times it by the inverse, why are we doing it by the inverse? Remember, if you do the inverse times another matrix, it equals to identity. And if it equals to identity, this destroys, right? That's what we want. We want it to technically equal to 1, kind of. So this destroys. But because we did that, we have to do it on this side. There. We have your first ever machine learning algorithm, which is linear regression. And parameters, the parameter is equal to x transpose t inverse x transpose y. And this is how you get your parameters using linear regression. And or you can call it least squares, okay? So we're going to, we're going to extend this concept, right? This is what you learned probably in maths in 2541 or linear algebra and stuff. So okay, you kind of learned this, right? So is this even, like, what's the whole point of this? So what we can do is we can kind of extend the concepts. I don't think so you probably haven't learned this. Okay, so we have this equation. You have this equation, the parameters, right? The parameters, and we're going to call this hat, right? Parameters hat, which means estimator, right? We estimate the parameters. It's not the real parameters. And this is x transpose x inverse x transpose y. And we proved that, remember? We proved that this is correct. Now, what are we going to put in the x? Right? Are they just going to be apples and oranges? Right? 0, 1, 2 and 0, 1, 2. We can have that, right? So oh yeah. Okay, so if we have this, we can do something cheaty, okay? So step 1, we need to add a bias term. Okay? So what a bias term does is pretend if I have a line, right? But in fact, when I do the linear regression formula, the real line actually looks like this. Okay, that's the real line. This is the real line. How are we going to shift it up? What are we going to do to make a shift up? Does anyone have any suggestions? How are we going to capture this shift? Every single point shifts up.
Add a constant.
Add a constant? Well, where are we going to add the constant?
At the end.
At the what?
At the end.
Where's the end?
To the equation of the line.
Okay, so what are we going to do? Okay, yeah, that's right, add a constant, but what constant? We need to find the constant. You don't just add a constant. But what are we going to do? How do we change this matrix to add a constant? We just add 1, 1, 1. We tack on 1, right? And because we tack on a 1, what does the equation look like? It will be something apples, right? Plus something oranges, plus something, plus something times a 1. And that is your bias term, right? You have to put 1, 1, 1, 1, 1. That is your bias. Now, that's okay. I think you also learned this in linear algebra or some other maths courses. Now we're going to do something different. Okay. So this is linear regression, right? But it doesn't actually mean linear. You can do quadratic regression, or you can do whatever regression, right? So what linear actually means is that the distance, the word linear comes from the fact that if I have like some, if I draw a line, right? It's not actually the line, that's why we call it linear regression. It's the distance that is linear, right? So if I just fit a line that looks like this, right? Why is it called linear regression? It's this. It's the distance it's a line. The distance to the line is a line. That's why it's linear regression, right? If I draw a parabola, if I use the same method to make a parabola, right? And let's say that the points are here, just pretend, right? Why is it called linear regression? Well, the distance from that. We are trying to optimize for the best distance, right? The shorter the distance, the better. That's what this algorithm does. And we're trying to minimize this vertical line distance. And that's why it's called linear regression. That's called, okay. But how do we do a parabola? Right, this is a line. We derive the equation for a line. How do we extend this to a parabola? How do we find a parabola? Well, remember before, if we want to add a bias term, we do this. So how do we do a parabola? Easy. We just get the first column, right, we just square it. We get the second column and we just square it. And now you have a parabola. This matrix will be a parabola. And if you want a cubic, well, we just cube it. We just keep adding columns. We just, so 2 cubed 8, and so on, right? So we can fit a quadratic, we can fit a cubic, you can fit whatever you like. There's one more thing. What happens if you don't want to fit it like that? Okay, this is probably the most important part. So if you didn't get anything else, this is the most important. So, obviously in real life, it's never going to be something apples plus something oranges, right? It's never going to be like that. It's equal to happiness. Sometimes it could be this. Something times apples times oranges equals to happiness. It could be this, right? Or it could be the sine of the something sine apples plus the something exponential of the apples plus something blah, like apples times oranges is equal to happiness, right? It could be all of this. So how do we do this inside the equation? Similarly, what do we do? Well, because apples times oranges, remember it's 0, 1, 2, 0, 1, 2. What we do is we make a new column, right? And what's the new column? 0 times 0, 0. 0 times 1 is 1, and 2 times 2 is 4. That's what we do. We capture this in the apples times oranges. That's what we do. We just literally times it across. How do we do sine? Well, we just do sine 0, sine 1, and sine 2. Right, and so on. How do we do exponentials? We just put an exponential of 0, e to the, yeah? And if it's logarithms, we just do ln. Obviously that's not allowed, but yeah. You get it? So what we do is we just change the matrix to follow what you want. Yeah. We have 5 minutes. Okay, so I think, so next week we're going to talk about how to actually implement it in your computer. But we'll be using the library NumPy.
And the Boston.
Yeah, the Boston housing. Yeah. Okay, so in NumPy, so I'm not going to do it now. But anyways, in NumPy, if you use, have you guys used MATLAB or like Maple or something? And other, those. It's kind of the same. The only difference, so to just remember this, to transpose something, to to make a matrix, we just do this. So step 1 is to import your library, right? Import numpy as np. Okay? So what does import? Import means to, well, literally import your library, right? And the library is called numpy. But we don't want to reference numpy every single time. So we make it as np, right? We change the name to np. So np is a standard in data science, they just call it np. You can change whatever name, like num or py. But normally when you see np, it's np. And what we do, when we want to make a matrix, right, we just do A is equal to np dot, right, np dot matrix. Right, we want to make a matrix, so you just do np dot matrix, and we literally just write your matrix. Right, you do brackets, big brackets. When you do that, you just write your matrix. So like 1, 2, 3. 1, 2, 3. In NumPy, these are multi-dimensional arrays, so you have to, at the beginning, you have to do double big brackets, okay? And then you do 1, 2, 3. So this is your first row. Your second row, you do comma, and then you go to the next one. And so on. Okay? So you have to put double big brackets at the end. So to transpose it, you just do A dot T. A dot big T, and you transpose the matrix. So that's NumPy. In MATLAB or whatever, it will be A dash or something. Similar, it's just A dot T. To multiply matrices in Python, it's also easy. It's just A and B. Right? If B is a matrix, you just literally just do A, B. Or you can just do A times B. Using the time symbol on your keyboard. This will work. To find the determinant, it's just NP, right? Dot lin out for linear algebra, right? Dot determinant of A. And this will tell you the determinant. For inverse, NP dot lin out dot inverse. And these are the things we will use. And yeah, just remember, if the determinant is 0, the inverse will say there's an error.
Yeah, we'll determine this, we'll demonstrate this next week. And also, with regards to what Daniel said earlier, if the determinant of a matrix is 0, you actually can't find the inverse, but as he said, you can apply methods to find the determinant of another matrix. So you're not actually finding the inverse of a matrix with a determinant of 0. So no laws of math were broken today. You're essentially just manipulating a matrix with determinant 0 into another matrix,
Yep.
and finding the inverse of that. So you're not actually finding the inverse of a matrix with determinant 0.
Yep.
So that's not possible, and it never will be.
Well, technically, okay, yeah.
You're not finding.
Do it, Daniel. Don't do it.
You're not finding the determinant, the inverse of that matrix, because that's not possible. But you can change it.
Yeah, it's called, if you want to search it up, it's called PseudoInverse, okay? And you can find the inverse of a determinant equal to 0 matrix. This will be used a lot in linear regression when the matrix determinant is equal to 0, right? And if it does equal to 0, we can still find the parameters. And that's called pseudo-inverse. Yeah, okay. I think that's all for today. Thanks.
Isn't that last part breaking the laws?